to solve for the equilibrium constant K using K expressions, but sometimes we might not be at equilibrium, and so we will have to shift in order to produce the missing component or figure out how to remedy the imbalance in the equilibrium. So if you have a 0 as one of the initial concentrations of the reactants or products, we know that we just shift always towards that side. So you would add the X on that side. But if all the initial concentrations are not 0, then it becomes more difficult to determine. So in order to determine the shift with these cases, we use the Q, which is called the reaction quotient. So to determine the type of shift, you have to compare Q to K. Remember, K is the rate constant. So if Q is equal to K, then the system is at equilibrium and there's no shift. So that's just nice and easy. But if Q is greater than K, then that tells us that the initial ratio is too large, meaning that some products have to turn back into reactants. And so to do that, the system will shift to the left. Okay? And this all is because of the fact that when we solve for K or Q, that we would take the product's concentrations over the reactant concentrations. And so if Q is bigger, that means that the products have a bigger value. So then the ratio is too big, so we have to use up products to make the reactants bigger in order to make it balance out. Okay? But really, all you really need to know is that when Q is greater than K, you shift left. Okay? So if Q is less than K, that means that the ratio is too small, so we are going to shift right. And that's, again, because of our products over reactants. That means that the products are not big enough this time, and so then you want to shift to make more products to make that numerator bigger so that you can make it bigger. This is a nice little graph picture to help you. I did include it in your note packet to help you signify, see what to do in each situation. So, and whenever I compare Q and K, I always put Q first personally. It's difficult to do Q first, and then also because if you think about the less than or the greater than sign being an arrow, the shift is opposite of where it's pointing. So since the greater than is pointing to the right, you really shift left. So that's confusing. So don't think about it that way, but this is just something you're going to have to commit to memory. Okay? So let's see how that works in example 12. So for the synthesis of ammonia, which ammonia is NH3, you couldn't get that from the numbers, we've seen this equation a ton, where it's N2 plus 3H2 makes 2NH3. Okay, so they're saying at 500 degrees Celsius, the equilibrium constant is 6.0 times 10 to the negative 2. So at equilibrium, K is 6.0 times 10 to the negative 2. We want to predict the direction in which the system will have to shift to go back to equilibrium in each of these cases. So in your note packet, I separated them. They're not so separated here, but this would be the first case and this would be the second case. Okay? So what we're going to do is we are going to solve just as if this were a K, plugging in this information, but instead of solving for K, now we're going to solve for Q. And then we compare the Q value we solved for to that 6.0 times 10 to the negative 2. Okay, so this is for the first case. So Q is going to be the NH3 squared over the N2 concentration times the H2 cubed. Remember, order of operations when you type it in your calculator. Okay, so for that first set of data, be careful where you're plugging things in as well. So it'll be 1 times 10 to the negative 3 is the NH3. squared over, and 2 is 1.0 times 10 to the negative 5 times 2.0 times 10 to the negative 3 cubed. Okay, so be careful when you solve that out, but when I solved that, I got q to be 1.3 times 10 to the 7. And just like k's, q's don't have units. Very nice. Okay, so now we have to predict the direction that it will shift. So we have to compare our q value that we just solved for versus the k value, which the k value we just said before is 6.0 times 10 to the negative 2. So positive 7 versus negative 2 is extremely a lot bigger, so the q is greater than the k. And since the q is greater than the k, then just look up above in your note packet, and when q is greater than k, the system will shift left. So that is the answer for the first set of data, first set. Okay, so now let's do that again with a new set of data for number 2, for the second set of data. It's still products of reactants, it's still the same equation. So just plugging in that information in the correct spots, I've got 2 times 10 to the negative 4 squared over 1.5 times 10 to the negative 5 times 3.54 times 10 to the negative 1, which is just a fancy way of saying 0.354 cubed. Okay. And then when I solved this one out, I got 0.06 for my q this time. Well, it's nice when you have scientific notation, right? So if we put this 0.06 into scientific notation, that would be 6 times 10 to the negative 2. Yes, I know I did not keep the significant figures. My apologies. But then, so now, taking our q versus our k, if our q is 6 times 10 to the negative 2, and our k is times 10 to the negative 2, that means they're equal to each other. So in this instance, the equation, the reaction, is already at equilibrium, so there will be no shift. Because if it's already at equilibrium, it doesn't need a shift to get it back to equilibrium. What that means. Okay? So that is 7.8.